Let us start lecture 35. The course is phase diagrams in single component and binary systems, and today's topic will be condensed ideal solution, and today we will try to look at the graphical presentation of Gibbs free energy of the solution, okay, and also we will try to see the partial molar Gibbs free energy of the components in the solution. Okay. So, that will be the two topics we will consider here. In fact, in the last lecture what we have seen that graphically we can actually show del G mix, and then from del G mix at any point on del G mix in case of binary ideal solution, we can actually find out the values of those partial mixing quantities, okay, for A and B, since we have taken binary. So, today we will look at how the free energy of the solution looks like in a on a free energy versus composition plot. Okay. So, now if I try to look at the expressions, first let us show the expressions, write down the expressions for ideal condensed, or we can say binary solution of A and B. So, G solution is equal to X A G A bar plus X B G B bar. And remember, we are actually considering, what are the things we are considering? We are considering 1 mole of solution, okay, and temperature and pressure are constant. Okay. Now, we can also write down delta G mix equal to X A delta G bar M A plus X B delta G bar M B. These are all mixing quantities, and this can be written as, and so we can actually expand this particular equation, and now G solution, it can be considered as G M. In one of the lectures we have actually made it as G M, but now we are actually term it as G 2. Now onward we will consider this as G 2 for the solution, and this is for 1 mole equal to X A G A bar can be written as G A naught plus R T ln X A plus X B G B naught plus R T ln X B. Since we are talking about condensed phase, so then let us also take one more consideration. Let us take P to be 1 atmosphere. So, that means this G A bar and G A naught and G B naught are basically all are at standard conditions at any temperature T. So, G 2 can be written as X A G A naught plus R T X A ln X A plus, or we can put it plus X B G B naught plus R T X B ln X B. Then G 2 becomes X A G A naught plus X B G B naught plus R T X A ln X A plus Xb ln Xb. So, this quantity is nothing but delta G mix if we come from here. Okay. So, I can write G2 equal to delta G mix plus, so now let us understand this quantity. So, before mixing we have XA mole of A and XB mole of B. So, when you add together it yields me 1 mole. So, hence when we try to look at GA naught and GB naught, these are basically molar Gibbs free energy of 1 mole pure A and B. Is that correct? So, if it is 1 mole, then the before mixing, what will be the before mixing free energy of A and B separately would be equal to XA GA bar and GA naught XB GB naught. Okay. So, if we add them together, so it's basically nothing but Gibbs free energy before mixing, or we can say unmixed condition. So, this can be taken as G1. So, then this equation becomes G1 plus this. So, this is the equation we will be using very frequently in subsequent lectures. So, the final equation we are seeing that G2 is basically or Gibbs free energy of solution, G1 is the Gibbs free energy of unmixed state, and delta G mix is basically Gibbs free energy of mixing. So, now this can be presented on G versus X plot, G versus X plot. X is the mole fraction, G is the free energy. So, let us look at how it is reflected in that graph. So, now we are actually starting to, this is G1 plus delta G mix and we are taking binary. So, let us take a binary situation. Let us say this is 0. Now, delta G mix at particular temperature T is this. Okay. So, this is XB, this is pure A. So, that means XA equal to 1, this side is pure B, XB equal to 1. Now, so let us take another plot and then let me put these two values, this is GA naught, this is GB naught, and this let us consider for solid solution formation from solid pure A and B. So, that is the condition we are taking, fine. So, this is some arbitrary value of G, and let us say these are those values of G A naught and G B naught. Now, if I want to find out what is G1, G1 is a kind of straight line connecting these 2 points, and this axis is basically, or I can put it as G. Now, once I know G1, then what I can do at any composition, let us say if I want to take this composition and let me just take few composition, this 1, 2, 3, 4, 5 composition, at composition X and with that composition with respect to B. So, let us say this is XB1, this is XB2, this is XB3, XB4 and XB5. These are 5 compositions. So, those composition, if I try to find out what will be my delta G mix. So, delta G mix at XB1 is this particular value. So, this is delta G mix at XB1. So, similarly, all those quantities are corresponding to delta G mix at XB2, like this. It will follow till XB equal to 5. Now, G2 solution, which is solid solution, so I will put a small s indicating the free energy of the solution, since G2 is considered to be the solution free energy. So, that is to be, that means this delta G mix quantity at a particular composition is to be added to this value, because this is G1 at X1, XB1, okay, and this is nothing but XG1 at XB2. Like that way it will follow up till XB5. And in fact, if I consider the pure condition you see the delta G mix value at both extreme ends when XA equal to 1 and XB equal to 1, that is nothing but 0, because delta G mix under pure condition is 0. So, now once we consider this part, so it will start from here, and then from this point you add up this particular quantity. So, you go down, because that is in the negative side. So, it will go down. Let us say it comes here. So, the scale is chosen in such a fashion that this big line is actually coming as a small value. So, that is what we have taken another block or plot, and it will keep going down, and then at some point of time again it will keep going up. So, if you see those points, so let us reflect those points. So, let us, this point is coming here. So, this quantity is nothing but delta G mix at XB1. Similarly, here let us say it comes here. So, this quantity is delta G mix at XB2. Like that way, if we follow up like that, it will go like this, and then again it will start going up like this, and then okay. So, these are the star mark points I can connect. So, let me put it in red color. So, this is one point, this is another point, this is another, this is another, and this is another. So, if we join them, and this is one point, another point, which are basically coming when delta G mix equal to 0. So, G2 would be nothing but G1 at pure condition. So, if we join them, it comes like this. So, this is nothing but G2 solution. Okay. So, we could see that G2 solution is basically simply the arithmetic addition of G1 line at different conditions and delta G mix at those different composition, and with that we have to add up delta G mix at the same composition, and then we find all those locus points and then we join together, we get the plot for G2. So, if I try to see how the final plot would look like schematically, so this is my delta G mix and this is G A naught, this is G B naught, and since both are considered as solid, so I can take solid, here also solid. So, this is solid, this is solid. Now, after that I have drawn this rate curve like this. So, this is G2 solid and every composition if I need to find out at this composition what will be the value of G2, it is simply this plus this. Okay. So, this is G1, this is delta G mix at this composition. So, this G2 here would be G1 plus delta G mix. Fine. So, that means this rate line is nothing but the graphical plot for G2 solution. Now, we have to look at these two quantities. Interesting observation can be done there. So, if I try to look at G A naught, G A and G B naught, it can be considered as for solid as well as liquid. This can be considered for solid as well as liquid, since we are talking about condensed phase. Now, these two appearance, one of those can be taken as a reference point, and the best reference value can be considered as 0. So, we can assign one of those quantities, either G A solid or G A liquid can be taken as 0. Similar, it can also follow up with G A G B naught solid or G B liquid solid, but we have to have some logic in assigning that 0 value. So, the one of the logics that can be followed is basically considering the stable phase at a particular temperature of consideration. Fine. So, that particular phase free energy value can be taken as 0. So, let us understand this part bit carefully. So, let us, in order to do that, so it is basically assigning reference value of 0 to G A solid liquid or G B naught solid liquid. In order to do that, let us consider that T M B is greater than T M A, and remember these are all pure conditions. Now, if I try to plot, let us say this is G versus T, since it is a pure condition, I can plot for both and plot free energy versus temperature plot at a particular pressure, and then I can show these two temperatures. So, in order to show, let us say for liquid I draw this. Let us say this is the temperature corresponding to T M B, and here this is G B naught liquid and this is G B naught solid, because pressure is considered as 1 atmosphere. So, that means over the entire temperature range all will be standard states, but now I have to find out where I can assign the value of 0. Why we are doing that? Because that will help us in understanding the drawing of phase diagram. Okay. So, that is what we are trying to see how we can assign those values, and that assignment will not change anything. Our calculation will not change, and we will show it with our calculated data that right now you are putting some logic to assign some 0 value, but if you reverse it still the thing will remain same, because finally our interest is to calculate the difference of free energy, because absolute free energy we cannot find out. So, it is basically convenience that we some value would be assigned to 0. Now, in this case this what? So, let us put for the solid A and solid B, since we know that for A case melting point of A is less than melting point of B. So, that case it will be like this. So, this is let us say T m A and T m A, because why? At this point G B naught solid equal to G B naught liquid, that is what that point corresponds to melting point. Similar here also, that similar situation happens. Here we can say that G A naught solid, G A naught liquid. So, this point talks about that. So, that is what that becomes my thermodynamic melting point. Now, let us take few temperatures. One temperature we take here, which is less than, this is T1, another temperature would be melting point of Tm A, another temperature would be in between, this is T2, and this is the fourth temperature would be Tm B, and another temperature would be T3. So, actually T3 we are taking few temperature. What is the relation? T3 greater than TMB greater than T2 greater than TMA greater than T1. So, that is the relation, and we need to see the equilibrium hierarchy or the free energy hierarchy at all the temperatures, these 5 temperatures. Okay. So, let us take temperature T1. Okay. At T1, how this free energy hierarchy works. Now, at T1 we could see that G B L has the maximum free energy considering this plot, and remember these free energies are with respect to this graphical plot. Okay. So, we can take mod value if they are negative in nature, but at this moment we are just taking those values as per the graph. So, G B naught greater than G B naught S greater than A naught liquid greater than G naught A solid. So, these are the thing. So, now I can consider for this as well as this two consideration. Since at T1 I see that the standard free energy for B in the solid condition is lower than standard free energy of B in liquid condition. So, then I can actually assign G B naught solid can be taken as 0, and accordingly G B naught L will sit above. On G versus XP plot, we will show that G versus XP plot how it shows. So, now if I try to look at, so now let us say this is the B side, this is the A side. Now, I take, let us say this is my 0. Okay. Now, we see that G B S to be taken as 0. So, I can put this value as G B, this is pure B, this is pure A, this point. So, this is also 0. So, I can put it as S naught at T1, okay. And then correspondingly the B value, liquid value would be here, GB naught liquid. So, that is coming from these two quantities. Similarly, if I try to look at A, so the for A, GAS naught is actually can be taken as 0. Why? Because GA naught S, that a solid condition, has the lower free energy than A of liquid. So, this can be taken 0 and GA naught liquid will be placed above GB naught, GA naught, since we are talking solid. So, how it can be placed? So, this point, since we are taking referencing as 0, so this is GA naught solid, and then correspondingly, so this quantity would be GA naught liquid. Okay. So, now that way we are actually placing these quantities, fine. Now, similarly, I can actually go like this, that by looking at this free energy hierarchy for A and B separately, by looking at which one has the lowest free energy at that particular temperature for specific to A or specific to B, I can put that free energy value to be 0. Okay. So, that is the referencing. So, it will help us to calculate phase diagram. Okay. For example, let us say another particular condition which will be interesting, that is at TMA. Let us look at the free energy hierarchy. For GB naught L, still it will be greater than GB naught S. We are separately considering, so I can put separately GA naught liquid equal to GA naught solid. So, since these are equal, so I can take them to be 0, and in fact, I could see specific to at this particular temperature, these two quantities are greater than GA liquid as well as GA solid with the standard values. So, this can be assigned as 0. Now, here I would have to assign GB naught solid to be 0, because with respect to B, GB naught solid has the lowest free energy. So, if I try to plot over this XA XB equal to 1, XA equal to 1, so there this would be GB naught solid, and then here it would be GB naught liquid. But in case of A side, we will see that GA naught liquid equal to GA naught solid equal to 0. So, these two values are 0, okay, and this is also XP. Okay. Now, at T equal to T2, if I try to look at the free energy hierarchy, GB naught L is still greater than GB naught S with respect to this figure, but GA solid now would have higher free energy compared to GA naught liquid. So, in this case GA naught liquid will be taken as 0, and in this case GB naught solid to be taken as 0. So, if I try to plot over so this is 0. So, here still it will be GB not solid, and in this side GA not liquid has to be taken as 0, and correspondingly the GA not solid will be placed above GA not liquid, and here it will be G not B liquid. So, that is the condition we will have. So, this is the part where GB not liquid would be placed. At T M B, GB not liquid equal to GB not solid, and GA not solid is greater than GA not liquid. So, here I would consider this would be taken, both the thing will be taken as 0, but here GA not liquid should be taken as 0. So, if I try to show it over the same plot, XB equal to 1, XA equal to 1. So, that means both the pure sides. So, here it would be GB not solid equal to GB liquid. So, both are to be taken 0, and here 0, those are 0 values. So, here GA not liquid, and correspondingly I have to show GA not solid at this point. Now, the last temperature at T3, if I try to look at the free energy hierarchy, GB not solid is now greater than GB not liquid. So, here GB not liquid to be taken as 0, and GA not solid is still greater than liquid. So, GA not liquid to be taken as 0, because if I see here at temperature T3, I see that all those values are following this hierarchy. So, now if I try to show it over this particular plot, G versus X plot, XB on this way, XB equal to 1, XA equal to 1. So, here 0, both are 0 values arbitrarily taken. So, here GA liquid not equal to 0, and here now GB not liquid be taken as 0, and the solid will placed here, and here also the solid will be placed here. Okay. Now, where this particular position will be, that will be those positions of GB not solid and GA not solid with reference to GA not liquid and GB not liquid, that has to be decided on the basis of this particular plot. Now, this is a kind of a arbitrarily drawn plot. So, if we can take the CP values of liquid and solid for both A and B, we can actually plot the correct plot, how those lines, G lines with respect to T at a constant pressure would position on G versus T plot. But this, with the reference to this, the difference between those GB solid and GB liquid, or GA solid or GA liquid in the standard conditions, that difference will be decided by what is the gap between these two. Okay. That can be reflected over G versus X plot. Okay. So, this is interesting. With this reference, we will try to see how we can calculate molar partial quantities. So, we will consider that molar partial quantities in the next lecture, with this understanding how we place our free energies of pure conditions over G versus X or the G versus composition plot. So, let me stop here. We will continue in our next lecture. Thank you.